Hi, hello. For this video, we are going to discuss other types of amplitude modulation. Okay, so from our previous videos, we have discussed what we call the conventional AM. So what is the conventional AM? So conventional AM is our double sideband full carrier AM. Okay, so aside from the conventional AM that we have discussed previously, there are still several types of amplitude modulation, and we usually call them single sideband communication system. Okay, so our conventional AM has two major disadvantages. Okay, so usually the carrier power constitutes two-thirds or more of the total transmitted power. Okay, so majority of the transmitted power is placed or allocated for the carrier signal. Okay. However, as we also know that the carrier signal contains no information. Okay. So where are the informations? So the informations are located in the sidebands. So therefore, those power that are provided in the carrier are just simply being wasted. Okay, so another major disadvantage of a conventional AM is that it utilizes twice as much bandwidth as needed with single sideband systems. Okay, so as we all know, for the conventional AM, we are transmitting both the lower and the upper sideband. But we also know that the content of the upper sideband is just the same as the content of the lower sideband. So therefore, it just means that we're just transmitting the information twice, whereas we can just send just the upper or just the lower sideband, and the information is already provided there. Okay, so therefore our conventional AM is both power and bandwidth inefficient. Okay, so these are the and bandwidth and power are the two predominant considerations when we are designing modern electronic systems. Okay, so because of these disadvantages, we are going to be introduced to other types of AM and explain their advantages and disadvantages over conventional AM. Okay, so the first type of AM that we are going to discuss is what we call the AM sideband full carrier. Okay, so it's full carrier, or the SSBFC. Okay, so we have here the radio emission for an AM single sideband full carrier is H3E. Okay, so the single sideband systems was first mathematically recognized and understood as early as 1914. Okay, so in 1914 and 1923 was the first patent granted for a single sideband system. So the first successful communication link was between England and the United States. Okay, so there are different sidebands communications. Some conserves bandwidth, other conserves power, while some conserves both power and bandwidth. Okay, so for the single sideband full carrier system, so this requires only half much of the bandwidth as compared to the conventional AM. Okay, so when we speak of the conventional AM, we are referring to the double sideband full carrier AM. Okay, so this is a form of amplitude modulation in which the carrier is transmitted at full power, but only one of the sidebands is being transmitted. Okay, so therefore, we can see the spectrum and the relative power distribution for this one. So from the our bandwidth here is just from the FC to the upper sideband. So this is just our bandwidth. Okay. However, um the power for the total power here is equivalent to PC, the carrier power, plus m squared PC all over 4. Okay, so since our carrier is still included here, so it is still has the carrier and one of the sideband. Okay, so with 100% modulation, the carrier power constitutes 4/5 or 80% of the total transmitted power, and only 1/5 or 20% for the total power in the sideband. So if we're going to recall, for a conventional AM, 2/3 of the power is provided for the carrier, while 1/3 is for the sideband. So as we can see, if we're going to compare this with our conventional AM, we just conserve bandwidth here. But when it comes to power, the power for the double sideband full carrier is much better compared with the power in our SSBFC or our H3E. So H3E is the radio emission, if you can still remember, for a single sideband full carrier AM. Okay, so if you happen to encounter a problem that is H3E, so that is your single sideband full carrier. Okay, so another type of, so again, for single sideband the full carrier, um the 100, this is the 100% modulated SSBFC envelope looks identical to a 50% modulated double sideband full carrier envelope. Okay, so if we're going to recall, for a conventional AM, the maximum and the negative peaks occur when when the carrier and both sidebands reach their respective peaks at the same time, and the peak envelope is equal to the sum of the amplitudes of the upper and the lower side frequencies. Okay, so for single sideband full carrier, only one sideband is present. So it's either upper or lower. So therefore, the peak change in the envelope is only half of what it is with the conventional transmission. Okay? So the demodulated signals have only half the amplitude of the double sideband frequency wave. So the repetition rate of the envelope is equal to the frequency of the modulating signal, and the depth of modulation is proportional to the amplitude of the modulating signal. So as you can see, we have here a trade-off, okay? So this type of AM requires lesser bandwidth, actually just half of the bandwidth, but it produces a demodulated signal having a lower amplitude. Okay? So what is the advantage of having your bandwidth halved? Okay, so as we can recall, the noise, okay, or the total power noise is somehow related to bandwidth. Okay, so when we lessen your bandwidth, or when we halve your bandwidth, your total noise power is also halved, and if one sideband is removed, the power in the information is also halved. Okay, so therefore we just have the same signal to noise ratio. Okay, so another type of AM is what we call the AM single sideband suppressed carrier. Okay, so this is SSB SC. Okay, or its radio emission is J3E. So every time you encounter J3E, it means you have a single sideband with suppressed carrier. Okay, so the carrier is totally suppressed and one of the sidebands is removed. So therefore, for this, the total transmitted power is just the power that is allocated to your either upper or your lower sideband. So in this illustration, it is just the upper sideband. Therefore, the total transmitted power is equivalent to m squared multiplied by the carrier power divided by 4. Okay, so this requires half as much bandwidth and considerably less transmitted power. Okay, so we can see the frequency spectrum and relative power distribution for the single sideband suppressed carrier in this figure. Okay, so this figure is the waveform, which is simply a sine wave. Okay, so we don't have an envelope for a single sideband suppressed carrier. Okay, so because we remove the carrier, and your carrier and therefore your waveform is simply a sine wave at a single frequency equal to the carrier frequency plus the modulating signal frequency, or the carrier frequency minus the modulating signal frequency, depending on which sideband is being transmitted. So it's either the upper sideband or the lower sideband. Okay, so as you can see, the waveform is no longer in a form of an AM envelope. So we have another type of AM. We call this as an AM single sideband reduced carrier, or SSBRC. Okay, so its radio emission is R3E. Okay, so if you encountered R3E, so that is a single sideband with reduced carrier. So in this, one sideband is totally removed and the carrier voltage is reduced. Okay, so the carrier is not totally removed just like in the previous type, but the carrier voltage here is somewhat reduced to approximately 10% of its unmodulated amplitude. Okay, so the carrier is totally suppressed during modulation and then reinserted. So the reinserted carrier is also called pilot carrier. Okay, and the pilot carrier is already at a reduced amplitude, and usually it is being reinserted at the for demodulation purposes. Okay, so the total transmitted power is just 10% of the unmodulated carrier power plus the power in one of your sidebands. Okay, so the amplification of the carrier in the receiver must be sufficient to raise the level of the carrier to a value greater than that of the sideband signal. So this requires half as much as the bandwidth, and at the same time, it also conserves considerable power. Okay, so to demodulate, for the demodulation purposes of a single sideband with reduced carrier, the carrier must be separated, it must be amplified and then reinserted again at a higher level in the receiver. That's why it is also called an exalted carrier. Okay, so why is it called an exalted carrier? Because the carrier is elevated in the receiver prior to the modulation. Okay, so it is also called exalted carrier detection. Okay, so the type of demodulation that we have is the exalted carrier detection. So we have here an AM independent sideband, or ISB. So its radio emission is B8E. Okay, so a single carrier frequency is independently modulated by two different modulating signals. Okay, so we still have here um, uh, we still have here a form of a double sideband transmission. We still have a lower sideband and an upper sideband. So the difference is that we don't have the same information both for the lower and the upper sideband. Okay, so instead of just calling it lower and upper sideband, we call it channel A and channel B, because channel A contains different information for what is contained in the channel B. Okay, so this is a form of a double sideband transmission in which the transmitter consists of two independent single sideband suppressed carrier modulators. Okay, so the single sideband output signals from the two modulators are combined to form a double sideband signal in which the two sidebands are totally independent, okay, of each other. Okay, so they contain the information that they contain is not similar. Okay, so except that they are symmetrical about a common carrier frequency. So in this case, we conserve both the transmit power and the bandwidth. Why? Because using the same bandwidth with the conventional AM, you have already transmitted two different channels. Okay, so this is a technique which is being used in the US for stereo AM transmission, wherein one channel, the left channel, is transmitted in the lower sideband, and the other channel, the right channel, is transmitted in the upper sideband. Okay, so this is one type of AM. Another type of AM is what we call the AM vestigial sideband, or VSB. Okay, so this is a form of AM in which the carrier and one complete sideband are being transmitted, but only a portion, a vestige portion, or only a part of the second sideband is being transmitted. Okay, so the lower modulating signal frequencies are transmitted double sideband, and the higher modulating frequencies are transmitted single sideband. So usually the carrier is transmitted at full. The lower frequencies can appreciate the benefit of 100% modulation, whereas the higher frequency cannot achieve more than the effect of 50% modulation. Okay, so it's like the whole um uh lower sideband and a portion of the upper sideband. Okay, so this is being used. So one practical application for a vestigial sideband is the picture portion of a commercial television broadcasting signal, which is designated as A5C by the FCC. Okay, so um, television signals are being transmitted by FM and AM. So the video portion for AM, for television, so the audio portion is by FM, or frequency modulation, while for the video they make use of a special type of AM, which is the vestigial sideband AM. Okay? So this is how we compare, okay, the comparison of single sideband transmission to conventional AM. So we have here the comparison of the three common AM transmission system. So we have the AM, or the conventional AM, wherein you have your full carrier plus your two sidebands. So you have your two sidebands and suppressed carrier, and you have your single sideband with suppressed carrier. Okay, so the power conservation, power efficiency, okay, requires considerably less transmitted power. That is the advantage of your single sideband communication system. Okay, so the total power transmitted is necessary to produce a given signal to noise ratio at the output of the receiver. Okay, so in a conventional and useful means of comparing your power requirements and the relative performance of the AM system. So the signal to noise ratio determines the degree of intelligibility of the received signal. Okay, so for a double sideband full carrier, the repetition rate of the envelope is equal to the modulating signal. For a double sideband of suppressed carrier, it is equal to twice the modulating signal. And for a single sideband suppressed carrier, this is not an envelope anymore, but rather a single frequency sinusoid equal in the frequency to the unsuppressed sideband frequency. So the unsuppressed sideband frequency is either the lower or the upper sideband. So we have here the comparison of your single sideband transmission to conventional AM in terms of rated power in units. Okay, so a conventional AM wave with 100% modulation contains 1 unit of carrier power and 0.25 unit of power in each sideband. So for a total transmitted peak power of 1.5 units. So a single sideband transmitter rated at zero point 0.5 unit of power will produce the same signal to noise ratio at the output of a receiver as the 1.5 units. Okay, so this is the representation. Okay, so in here we have a term PEP, or the peak envelope voltage, or power rather. So the peak envelope power is the RMS power. Okay, the RMS power developed at the crest of the modulation envelope. So we have here the same performance is achieved with a single sideband suppressed carrier using only 1/3 as much as the transmitted power and half the bandwidth. Okay, so when we say crest, it means when the modulating signal frequency components are at their minimum amplitude. Okay, so we have here your voltage vector 100 at 100% modulation. So it requires only zero point 0.5 unit of voltage per sideband and 1 unit for the carrier with conventional AM for a total of 2 PeV. So PeV is peak envelope volts and only 0.707 PeV for a single sideband. Okay? So these are other comparison for a single sideband transmission to conventional AM. So in terms of RF envelopes, so in terms of the modulated information signal, okay, so the information signal is somehow lower in magnitude compared with the conventional AM. So the arbitrary noise voltage is somewhat improved when it comes to the single sideband because of the reduction of your bandwidth, and the signal to noise ratio is just the same. Okay, so we have here the advantages. Of single sideband transmission. So four predominant advantages of single sideband suppressed carrier or reduced carrier transmission over conventional AM. Okay, so the first is power conservation. So much less total transmitted power is necessary to produce essentially the same quality signal in the receiver as is achieved in conventional AM. Okay, so we have here bandwidth conservation. This requires half as much bandwidth as conventional AM double sideband transmission. So we have what we call selective fading, sideband fading, or carrier amplitude fading, or these are sometimes called transmission impairment. Okay, so if we have a carrier and you have two sidebands and they are being transmitted or propagated through a transmission media by different paths, okay, so we may experience different transmission impairments. So when your sideband followed a different path, so you call that sideband fading. So when your carrier followed a different path, and it's lost, so you call that carrier amplitude fading. Okay, so in this type of problem, so one sideband is significantly attenuated. But since in single sideband communication, we are totally eliminating the carrier or reducing it, and one of the sideband, so therefore the selective fading uh, is really being improved. Okay, and finally, noise reduction. Okay, so of course, half your bandwidth reduced, also half of your thermal noise power. So these are the advantages of your AM, for predominant advantages of your single sideband compared with our double sideband or conventional AM. Okay, however, there are also disadvantages. There are some disadvantages for single sideband transmission. Okay, so those disadvantages are, first, you have complex receivers. Okay, so single sideband communication require more complex and expensive receivers than your conventional AM transmission, because most single sideband transmission include either a reduced or suppressed carrier. Thus, envelope detection, which we discussed in the previous video, cannot be used anymore. And then we have of course, you have added cost, complexity, and size for a receiver. Okay, and then tuning difficulties. This requires more complex and precise tuning compared to a conventional AM receivers. Okay, so we have this might be undesirable for average user. However, these disadvantages can be overcome by using more accurate, complex, and expensive tuning circuits. So there are only two disadvantages, but we have several advantages. So there are more advantages compared with the disadvantages in using the single sideband communications compared to the conventional sideband. Okay, so this is for a conventional AM. How about what will be the total transmitted power if we're going to make use of a single sideband. So it didn't mention uh so a single if it is transmitted as a single sideband only. Okay, so we have here our supposed to be formula for this. Okay, so for us to transmit just a single sideband, okay, so the total power required for a single sideband is equivalent to m squared PC all over 4. Okay. However, we do not know yet the unmodulated carrier because in the problem, it is already the total power transmitted for a conventional AM. So in this case, we need to solve first for the carrier power. So how do we solve for the carrier power? So for our conventional AM, we have a formula that for a total transmitted power that is equivalent to the carrier power, 1 plus m squared all over 2. So this is for a conventional AM if you're going to recall the formula. Okay, so we need to solve for PC. Okay, so fully modulated. So what do we mean by fully modulated? That is our modulation index is equivalent to 1. So that is our uh, definition for fully modulated. So we solve for PC. So your PC is equivalent to 1,000 all over 1 plus 1 over 2 squared. So this is equivalent to 1,000 divided by 1.5. So that will give us 666.67 watts. Okay, so this is our carrier. Okay, so if we will be using this carrier, what will be the total transmitted power if we just make use of a single sideband AM? So for a single sideband AM, this is equivalent to m squared. So that is 1 squared multiplied by 666.67 divided by 4. Okay, so that will give you 666.67 divided by 4. So that is 166.67 watts. So that is the difference. So for a conventional AM, you need to transmit 1,000 watts. But for a single sideband transmission, you only need to transmit 166.67 watts. Okay, so that is the difference. Okay, so let's have another example here. So it says a single sideband transmission drives 121 volts peak, okay, into a 50 ohms antenna. Okay, so calculate the PEP. So what is your PEP? So PEP is your peak envelope power. Okay, so what is the range of the average output power? Actually, we have mentioned the PEP a while ago, and we said that. Okay, so what is your PEP? So PEP is your peak envelope power. So it is an RMS value at the crest. Okay, so we have mentioned that a while ago. Okay, so but what is given in our problem is a peak value. Okay, so your PEP is simply your RMS value. So PEP is equivalent to the RMS value. So what is the RMS value if we are given the peak value? So that is just equivalent to 121 divided by square root of 2 squared. Okay, so from peak, we just convert that to RMS. So uh, if the given in the problem is already in the RMS form, so we don't need to convert this anymore. So we just use this because we are given the peak value instead. Okay, so divided by R, so our resistance is equivalent to 50 ohms. Okay, so this is equivalent to 121 divided by square root of 2 squared divided by 50. So that will give us 146.41 watts. Okay, so we have a follow-up question. So it says here, what is the range of the average output power? So we are talking about a range. So what do we mean by a range? When we're talking about the range, we have a minimum and we have a maximum value. Okay, so for typical human speech, okay, so for a typical human speech, we have a p average. So we have a p average which is equivalent to PEP all over 4 to PEP all over 3. Okay, so PEP over 4 is the minimum range and PEP over 3 is the maximum range. So what do we mean by this maximum by this average value? So this is the voice amplitude peaks are produced only when very loud sounds are being generated during certain speech pattern, or when a certain word or a certain sound is being emphasized. Okay, so for normal speech levels, the input and output power levels are usually less than the PEP. Okay, so the average, if you encountered problems like an average output power, usually it is PEP over 4 all over and PEP over 3. So in this type of problem, it is simply 146.4 divided by 4. So 36.6 to 146.41 divided by 3, 48.8 watts. So this is the average, okay, for human speech. So this is usually the average being used for human speech. Okay, so let's have another example. So we have here determine the power saving. Okay, so determine the power saving in percentage. Okay, how much power did we save? Okay, so determine the power saving in percentage when the carrier is suppressed in an AM signal modulated to 80%. Okay, so what do we mean by that? How are we going to represent the power being saved for a conventional AM and um for a single sideband suppressed carrier? Okay, so it doesn't, it mentioned just a suppressed carrier. So we didn't it didn't mention that you have a single sideband. So it just says here when the carrier is suppressed. Okay. So first thing is we get first the total power transmitted. So we get the total power transmitted using conventional AM, and that is equivalent to PC 1 plus M squared all over 2. Okay? So our M is 80. So this is zero point 0.8. So this is PC 1 plus zero point 0.8 squared all over 2. So that will give us zero point 0.8 squared divide by 2 plus 1. So for a conventional AM, our total transmitted power is 1.32 multiplied by your PC. Okay? So if we suppress your carrier, that means we are just transmitting your two side bands. So our total transmitted power if we suppress your carrier is equivalent to M squared PC divide by 2. So why not divide by 4? So divide by 4 is being used if we have suppressed also one of your sideband. So in this case, we are transmitting both of the sidebands and we are just suppressing the carrier. Okay, so substituting here, you have zero point 0.8 squared all over 2 multiplied by your PC. So the total transmitted power for a suppressed carrier is equivalent to zero point 0.8 squared divided by 2. So that is equivalent to 0.32 of our carrier power. So how do we solve for the power saving? So the power saving is equal to the power being transmitted using the conventional AM. Okay, so using the conventional AM minus the power being conserved using your suppressed carrier divide by the total power using your conventional AM multiplied by 100%. So that is equivalent to 1.32 minus 0.32 all over 1.32 times 100. Okay? So we have there 1.32 minus 0.32 divided by 1.32. So that will give you times 100, 75.76%. So this is the total power that was saved when we transmit your AM using a double sideband suppressed carrier compared with the conventional AM having a full carrier. So you have a power saving of 75.76%. Okay, so that is how you do that. Okay, so what if you transmit it using a single carrier only? So you just make use of m squared PC over 4, because if that is the case, you are just transmitting only a single sideband. Okay, so let's have another example. So we have here a double sideband system must suppress the carrier by 50 dB from its original value of 10 watts. Okay, so to what value must the carrier be reduced? Okay, so we need to suppress, or we need to reduce your carrier. Okay, so how much? To what value must the carrier be reduced? Okay, so what is our formula for that? Our formula for that is just your simple decibel formula. So that is just a simple decibel formula. Okay, so your S here in terms of dB, or your suppression in terms of dB, is equal to 10 logarithm of the original, okay, original power all over the reduced power. Okay, so how much it is to be reduced so that we can suppress your carrier by 50 dB. So therefore, this is equivalent to 50 dB, 10 logarithm of the original power, which is equivalent to 10 watts, and we wanted to solve for the reduced value. Okay, how much was the reduced value of your carrier? Okay, so solving for the reduced value, so this is equivalent to 10 watts divided by the anti-logarithm of 50 dB divided by 10. Okay, so that is equivalent to 50 divided by 10 anti-logarithm divided by 10 watts inverse. So that will give you what? 100 microwatts. So from the original 10 watts, you have to reduce that to 100 microwatts so that you can have a suppressed carrier equivalent to 50 dB. Okay, so those are the types of problems that you might encounter, okay, when talking about single sideband communication. Okay, so how does a single sideband transmitter looks like? So is it very very different from the is it very very different from the transmitter of a conventional AM? Okay, so actually, just like a conventional AM, it also has an audio input, that is your modulating signal. It also has an oscillator for your carrier. Okay, so what is the difference? Instead of passing through a simple modulator circuit, we have a new items here that we can see, no, that we didn't encounter previously. So we have here the balance modulator. We have already IF before, so we have a balance modulator here and a band pass filter. Okay, so what are the additional circuit for a single sideband AM transmitter? Okay, so the first is your balanced modulator. Okay, so the balanced modulator is one of the most popular and widely used the balance ring modulator is one of the most popular and widely used balance modulators. Okay, so it is sometimes, sorry. So it is sometimes called balanced lattice modulator. Okay, so this is a circuit that generates a double sideband signal, suppressing the carrier and leaving only the sum and difference frequencies at the output. Okay, so the output of a balanced modulator can be further processed by filters or phase shifting circuitry to eliminate one of the sidebands. So if we make use of a balanced modulator, we are just eliminating only the carrier. So we still need to have another or additional circuit so that we can eliminate one of the sidebands. Okay, so there are different types of balance modulators, which includes the lattice, which we're going to discuss for today, and then we have the 1496-1596 in the form of an integrated circuit, and we also have an analog multiplier. Okay. So this is how the operation of a balance modulator. Okay, so as you can see, you have here your T1. So your T1 is your input transformer. Okay, so wherein your modulating input is being applied. And then we have here your T2. So your T2 is your output transformer where we get your double sideband output. Okay, we have four diodes here. So your four diodes are connected in a bridge circuit. If you can still remember your bridge circuit, um, the carrier is being coupled or being applied. So this is your carrier oscillator. This is being applied on the center top of the input and output transformers. Okay, so your modulating signal is being placed at the input transformer and your output at the secondary of your second transformer. Okay, so this is your this is your oscillator carrier signal. This is your modulating signal, and this is the output of our balanced modulator. Okay, so we have here the different operation. So for this one, for a positive carrier oscillator, okay, so your carrier is a sine wave, usually of higher it is of higher frequency and amplitude compared with the modulating signal. Okay, so this is used as a source to forward and reverse bias your four diodes here. Okay, so that means the carrier oscillator or the carrier signal is the one responsible in turning your diodes either on or off at a very high rate because of the very high frequency. Okay, so your diode acts as a switch that connects the modulating signal. So it connects the modulating signal at the secondary of your T1 to the primary of your T2. Okay, so how does this operate? So when the modulating signal is zero, so let us say no applied signal here, and our carrier is positive, like this one, plus and minus, as you can see, the diode, your diode 1 and your diode 2 are both forward biased, okay? While your diode 3 and your diode 4 are both reverse biased. So that means your diode 3 and your diode 4 are open circuit. Okay, so the two currents, if we're going to follow here, we have two currents. So the currents are divided by the center top, so it's placed at the center top. So your current divides equally in the upper and lower portion of the primary winding of our T2. Okay, so the current in the upper part of the winding produces a magnetic field that is equal and opposite to the magnetic field produced in the lower half of the secondary. So since they are equal in magnitude while oppositely directed, they simply cancels each other. Okay, so the carrier signal simply cancels out. So that is how you eliminate the carrier using the balance modulator. Okay, so therefore, no output is induced in the secondary because we don't have a modulating signal yet, and the carrier, of course, is effectively suppressed. Okay, now, what happens when the polarity reverses? Just like in this one. So it is minus and plus. So in this case, your D2 and D1 is the one which are for reverse biased, while your D3 and D4 are the one which are forward biased. And the same. What happens in our first case also happens in our second case. Therefore, for a balanced modulator, your carrier is effectively balanced out and your output is totally equal to zero. Of course, the degree of the carrier suppression depends on the degree of precision of your transformer. Okay? So, on our goal is to have an equal upper and lower currents and perfect magnetic field cancellation. And the magnetic field cancellation, of course, depends on the transformer that you're going to make use, and also the placement of your center top. So it must be really centered so that the upper and the lower magnitude will be the same or equally the same. Okay, so what happens now when a modulating signal is applied? So it is no longer equal to zero. So what happens? So when there is already a modulating signal, so simply your diode acts as a switch. So for forward biased, okay, so for forward biased and you have a modulating signal, so you can have an output at the secondary terminal of your transformer 2. Okay, so the diode switches connect the secondary of T1 to the primary of T2 at different times depending on the carrier polarity. So therefore, it depends on the amplitude and phase in the modulating signal that will also be your output. Okay, but we have a phase reversal here. As you can notice, we have a phase reversal here because center top produces 180 degrees phase reversal. So if our input is positive half, so our output will be negative half. And if our input is negative half, our output will be positive half because of the phase reversal being introduced by your center top transformer. Okay, so here are other ways of eliminating our carrier. So these are other balanced modulator circuit. So this is already in the form of an integrated circuit. Okay, so the output of a balanced modulator is still double sideband. Okay, we just removed the carrier. Okay, so the transmitters used for single sideband suppressed carrier and the single sideband reduced carrier transmission are identical, except that the reinserted carrier transmitter have an additional circuit which adds a low amplitude carrier to a single sideband waveform after suppressed carrier modulation has been performed. Okay, so we have here the different techniques. So the first technique is what we call the filter method. So the filter method is considered the simplest and most widely used method. Okay, so as you can see, you have here your carrier, and then you have here your audio amplifier in a form of a microphone, usually a voice. Okay, and your crystal oscillator here, usually provides your carrier signal. Okay, so they pass through a balanced modulator circuit. After passing through a balanced modulator circuit, you have a double sideband signal. Okay, so where is the carrier? It was already suppressed in the balanced modulator. Now, for the sideband filter, we can make use of uh, a highly selective bandpass filter that selects either the upper or the lower frequency. Okay, so if we choose the upper sideband, therefore it will only pass the upper sideband, or if the lower sideband, it will only pass the lower sideband. So the output for a sideband filter is your single sideband signal. Okay, so amplifying it further using your linear power amplifier before being transmitted through free space. So the output of a balanced modulator is a double sideband signal. An SSB signal is produced by passing the double sideband signal through a highly selective bandpass filter. Okay? So with the filter method, it is necessary to select either the upper or the lower sideband. So filters used for single sideband have higher Q compared to LC filters. So we have already discussed filters from our previous discussions. Okay? So there are two methods for selecting the upper and the lower sideband. Okay, so it's either we make use of two filters. Okay, so we just switch in between those two filters, or we make use of two different carrier oscillators. So one carrier oscillator can produce the lower sideband, and another carrier oscillator which can produce the upper sideband. Okay, so another type is the phasing method. Okay? So, for the phasing method, this uses a phase shift technique that causes one of the sidebands to be canceled out. Okay? So, your carrier oscillator is being applied to the balance modulator. You have two balance modulator here. So balance modulator 1 and balance modulator 2, and we have a phase shifter here. Okay, so phase shifting can cause one sideband to be cancelled out. Okay, so how are you going to cancel out one of the sidebands here? Okay, so let's discuss this. So as you can see, you have two inputs, okay? So the carrier and the modulating signal. So our carrier is VC sine of 2 pi FCT, and our modulating signal, which is your VM sine of 2 pi FMT. Okay? So the product or the output of our balanced modulator is equivalent to the product of these two, which is equivalent to VC um, sine of 2 pi FCT times VM sine of 2 pi FMT. Okay, so this is the product of your balance modulator 1. So recall, okay, from our trigonometric identity, we have sine A, sine B. Okay? When we have sine A and sine B, what is this equivalent to? So this is equivalent to 0.5 cosine of A minus B minus cosine A plus B. Okay, so to write our equation here, so this is equivalent to 0.5 sine of zero point 0.5 Vm VC, their amplitude, cosine of 2 pi FC minus 2 pi FMT minus cosine 2 pi FC plus 2 pi FMT. Okay, so this is for our first balance modulator. Okay, so before your modulating signal enters your second balance modulator, and before your carrier signal enters your balance modulator 2, they will be passing through a phase shifter, a 90 degrees phase shifter. So what do we mean by a 90 degrees phase shifter? So that only means that if we have a sinusoidal waveform, upon passing through a 90 degrees phase shift, okay, so this is equivalent to what? It is it is now equivalent to a what? Cosine waveform. Okay, so cosine value is cosine is the result when you shift your sine wave 90 degrees. Okay, so cosine leads sine waveform by 90 degrees. So therefore, upon passing through the 90 degrees phase shifter, your two signals becomes VC cosine of 2 pi FCT and VM cosine of 2 pi FMT. Okay, so again, trigonometric identities. So we have cosine A, cosine B. That is equivalent to what? So that is equivalent to zero point 0.5 cosine of A minus B plus cosine of A plus B. Okay, so further elaborating this formula, you have zero point 0.5 VMVC cosine of 2 pi FC minus 2 pi FMT plus cosine of 2 pi FC minus 2 plus 2 pi FMT. Okay, so this and this will go to your summing point. Okay, so you will be adding these two. Okay, so upon looking at this figure, upon adding these two, we can see that your cosine here will be cancelled out with your sine here. So what will be left is just the lower sideband frequency, or FC minus FM. So that is how your phasing method operates. Okay, so we eliminated the upper sideband and we retained, or we transmitted the lower sideband. Okay, so for phase shifters, we usually make use of RC networks. Okay, so RC networks are being used as phase shifters. Okay, so the phasing method of single sideband generation uses a phase shift technique that causes one of the sidebands to be cancelled out. So the phasing method uses two balance modulators which eliminate the carrier, and the carrier oscillator is applied to the upper balance modulator along with the modulating signal. So the carrier and the modulating signals are both shifted in phase by 90 degrees and applied to another balance modulator. So phase shifting causes one sideband to be cancelled out, particularly the upper sideband, when the two modulator outputs are added together. Okay, so what is left is the lower sideband. So we have the third method. So the third method is somehow just like the phasing method, but a more improved phasing method. Okay, so we call this as the Weaver method, or the third method. Okay, so also it is about phase shifting. Okay, so it says here the so-called third method of single sideband generation developed by D.K. Weaver in 1950s. I was trying to search for the complete name of D.K. Weaver, but I cannot find it in the internet. So it's just D.K. Weaver. It's written there. So it's similar to the phase shift method described previously. in that it uses a phase shifting and summing to cancel the undesired sideband. Okay, so however, it has an advantage in that the information signal is initially modulated onto an audio subcarrier, thus eliminating the need for a wideband phase shifter, which is difficult to build in practice. Okay, so but the operation is somewhat similar uh, to the phase shift method. Okay? So for the synchronous detection amplitude detectors, so we use a synchronous or the heterodyne receivers for or the non for the coherent, the asynchronous or non-coherent for um the conventional AM. For this single sideband communication, we make use of synchronous detection. Okay, so the synchronous detection. So the synchronous detection uses an internal clock signal at the carrier frequency in the receiver to switch the EM signal off and on, producing rectification similar to that in a standard diode detector. So synchronous detectors or coherent detectors have less distortion and a better signal to noise ratio than standard diode detectors. Okay, so the key to making the synchronous detector work is to ensure that the signal producing the switching action is perfectly in phase with the received AM carrier. An internally generated carrier signal from an oscillator will not work. Okay, so this is a practical synchronous detector. So they are also called coherent detectors or homodyne. Okay, homodyne detectors. So the center top is being applied. So the clock is being applied in center top between D1 and D2. Okay, so the D1 and D2 here, your diode is acting like a switch. Okay, once it is forward or reverse bias. So it is somewhat similar to the operation of a rectifier circuit. Okay, so double sideband and single sideband demodulation. So a balanced modulator used as a product detector. So any balanced modulator can be used as a product detector to demodulate a single didn't move. So any balanced modulator can be used as a product detector, okay, to demodulate a single sideband. Okay, so you have the output of a balanced modulator is a suppressed carrier, and then passing through a low pass filter, we have a single sideband output. Okay, so the recovered intelligence signal. Okay, so those are the different types of single sideband communication. Okay, so um, that's it for our AM. Okay, so that is for single sideband AM. Thank you very much for watching, and don't forget to hit the like button. Okay, so God bless you all. Thank you.